that will adjust its capacitance according to the moisture-induced antenna impedance changes. And finally, the sensor output, in this case the sensor code, will retrieve at the reader in real time. This is the 3D exploited view of our antenna design. It consists of a short-ended patch antenna, and this is the top layer, short-ended, to the bottom layer, and the antenna is mounted on a thin Teflon substrate of 1 millimeter. So the Teflon substrate has been mechanized to embed an absorbent fabric patch which will contain the liquid, the water in this case, and an inlay of a network of holes has been opened in one of the top of the bottom layers to allow for infusing the water or letting it evaporate during the drying process. So here in this video you can see how all the spars are assembled together. And basically we have a final prototype of 1 millimeter thickness and 50 millimeters times 30 millimeters. So in order to model the dielectric behavior of the absorbent when it's containing different levels of liquid, we were using mixing rules. In this case, specifically power loss, because they have a nice analytical form that, let's say, it's easier to work with when we try to solve for different parameters. So basically, they relate the volume of a mixture to the permittivity of a mixture to a power beta, to the sum of the different components, the volume of the different components and the permittivities to the power beta again. This beta parameter is the power that gives the name to the power loss, and it's found experimentally for different antennas or different absorbents, materials. So in this case, the absorbent will be modeled as a mixture that is comprised at least two different components. A structure, in our case, will be textile fibers, and the pores, which is a network of holes that can contain different fluids. Normally air, but in our case will contain a mixture, a combination of liquid and air. So in the beginning will contain all liquid, and then it will start evaporating and it will start being filled with air. So for simulation purposes, we can use this formula and compute the mixture permittivity for different liquid volumes and air volumes. So, and this formula can also be arranged in different ways. So it allows us to compute the liquid permittivity to, for instance, for identification of liquids in different applications. But also, we can use it in capacitor sensors to compute the liquid volume using the mixture permittivity given by the parallel plate capacitor formula. So now we know how the dielectric properties of the absorbent change depending on the amount of liquid that is in the absorbent. And here I'm going to show how the integrated circuit, self-tuning integrated circuit, tracks the variations in the input impedance. So we're using Axon Magnus S3, and the self-tuning integrated circuit selects the capacitance. No, it has a range of operating capacitance, and it will select the capacitance for which it receives the maximum amount of power. So this can be expressed according to this formula, which says that the selected capacitance in this range, in the range that the operating range of the microchip, is the one that maximizes the power transmission coefficient for a specific frequency and for a specific water mass in the absorbent. So here we see how an absorbent can be filled with 100% water, and during the evaporation process, it gets dry, and all this, so the absorbent is represented, the structure is represented as this orange box, and the holes represent the pores that are filled with water, and they start evaporating until it reaches the dry state, the empty state. So here, I'm showing you the different simulations for different amounts of liquid in the absorbent. as you see, for instance, in the case of the initial state where the absorbent is fully filled with water, we see that the microchip will sweep the capacitance value, the internal capacitance value, and will measure the amount of power that is received by the chip. And then it will do it for each of the points that it can measure the power by changing the number of levels that the capacity it can program, right? And it will select the one that gives the maximum power, so the peak of these curves. So when the water starts evaporating, we have these different curves, right? And at each curve, we know that the chip will select the value of the capacitance that provides maximum power. Okay? So now instead of having just 5 discrete water levels, we have a continuous amount of simulations. Let's say here I'm showing 400 water volume simulated levels, where you can see that each column here, its vertical line corresponds to a single curve in the previous slide. And here, the peaks are represented by the power transmission coefficient value equals to 1. So it means that we can track these maximum peaks here with the white dashed line. So this, as you see in this figure, I'm showing you the water going from 100% to 0% also, and the capacitance range in the vertical axis. So this dashed line, this white dashed line, gives us the capacitance that the chip will select for all the different levels of water. And in the continuous line, we have a linear model that we will use later on for transforming the sensor code into the mass, the water mass loss. So here I'm showing you the prototype, fabricated in our laboratory. As you see, we have an inlet of holes opening this disposable copper tape, which means that we can also replace the absorbent for different applications and reuse the tag, the rest of the tag. We can reuse the Teflon slide, the antenna, and also the copper, and also the microchip. And we also need to change this small disposable copper tape, and the absorbent. Imagine that we're analyzing different liquids like sweat or oil or other liquids. So it's, let's say, it's to make the antenna reusable very easily. Here I'm showing the setup for the measurement. As you see, we were infusing the water with a syringe through the sweat inlet, through the water inlet, and then letting it evaporate and continuously interrogating the tag to receive the different sensor codes. So basically, we did this experiment for 3 different materials: cotton, polyester, and denim. And we were, like I said, we were measuring the sensor code for each experiment, right? And the experiments lasted close to 10 hours for the drying process. And you see that for each different material, they behave differently. They provide different curves. And then we use the linear model here to convert the sensor code or the capacitance to the mass inside the absorbent. Then this is something that we are working on now. We want to calibrate the sensor, and we're using Newton's law of cooling applied to mass transfer to, which in our case simplifies to an exponential decay, to fit the exponential parameter gamma, and then compare different methods using this exponential parameter. So now we wanted to assess the performance of our sensor, let's say accuracy, or how far we were from traditional methods such as the gravimetric measurement. So what we did was taking a gravimetric experiment where we had a 30 centimeters times 50 centimeters denim fabric that we were measuring on a scale, and we were measuring the water mass loss in this fabric. The results are shown here as a light blue continuous line. And also we can see that we fitted the exponential decay model, providing this specific gamma. And then simultaneously, we were measuring the evaporation using our sensor. And this gave us the dark blue continuous line, which we also fitted to the sensor, to the Newton's law of cooling applied to mass transfer, and it gives us a different gamma. So we see that both measurements, the gravimetric and the sensor, differ considerably, and we wanted to understand why. So we found out the most probable reasons were two. First one is that the impedance matching is not a linear process. The impedance changes may not track the evaporation process accurately. And also, we need to consider that the experimental conditions were different. Because in the gravimetric measurement, the piece of fabric was left in open air for evaporation. But in our case, we have the fabric embedded in between the metal, and also only has some inlay of holes for the evaporation, which may change the environmental conditions of pressure. And so we think that these are the two most feasible reasons why this deviation occurs. But this is also for future work. So finally, let me conclude by saying that the proposed sensor can track the water evaporation in different fabrics while maintaining grid ranges close to 2 meters. It provides high frequency resolution and adjustable bandwidth that maximize the sensor resolution. It's adjustable and flexible and low cost and low profile. And our future work will consider finding a calibration process to minimize the error and validating the solution in real environments. And